Um,
It's gonna be okay. It's fine. It's really sad.
I never had a week.
Oh. So I remember that going additional homework in lab report helps me. Yeah, I will be delighted to read next Wednesday. And on the, I think everyone collected. There was one person that's still thinking about the direction of research project, and it's okay. We'll start actively working on it on common Wednesday night. So, how can we enjoy the remaining 40 minutes of the lecture? What are the goals, expectations, and possible outcomes? So we are interested in support. The goal is to predict outcomes from the scientific instruments for measurement of properties of molecules. Molecules contain elements which are characteristic of fluid nature, and when you are trying to apply this laws or mathematical description for the nature of outcome to simple, a little more complicated approaches. Not only we recently recognized that not only electrons have way of nature, but also nucleus, business programs, and we are investing your precious time into so-called harmonious state, or something else. But through the lab, which you enjoy in the form of the book right now, you already know that it oscillates, goes in distribution center, and the uncertainty also oscillates twice. If we get to the stage by pen and paper, we should be very happy. As always, navigation modeling is much more easy for operator than actual derivations. But since it is there was a little education component in the good background, if you try to do it on the board, memorize maybe some key steps. So how can we formulate the board? To obtain mathematical support for oscillatory behavior of the Gaussian effect in the harmonic potential. Right? How were we solving problems with this in the past? When we had the particle results. How many ways to predict the future do you know? Huh? Okay, I know three. I know three as well. Maybe someone knows more. So what's the third way? You all know me. You don't tell.
You already said that.
No, I didn't. You are ahead of me. So I can state expansion with some expansion coefficients and phase accumulation for which I can state, right? And then if you have super, it's pity that recordings went on the web, but we had a really good time in discussing the deep question posed by John. Yes, I will look in for web packet not new. Bless you. You don't have.
There's something in this room. Every time I'm here, I sneeze.
No, it's an allergy to quantum theory.
Is that?
Please, no quantum anymore. So, if the system is prepared in one of the eigenstates, it will not change. But if you are looking for something to move, it means it will be superposition of several eigenstates. We already know eigenstates through the application of raising and lowering operators. Okay? Lowest operator Gaussian, next it's like camels with increasing number of arms. And we also need you to enter the class 4. So we also need, if our prediction of future includes eigenstates, eigenenergies, accumulation of phase, and expansion coefficients. Okay. We already know eigenstates. Now we don't need eigenenergies. Okay. And then expansion coefficients. So basically, it's the general direction for us to discuss. Basically. So very local target will be energies of eigenstate. And I did violate my own rules. But, I didn't attempt to rewrite everything literally with logic standing on the fundamentals without rules. There were some steps that were introduced rather than I was arguing to you rather than strict mathematical logical agreement. It is done just to shorten the time. If anyone waits, so one of these steps which were not fully covered was related to eigenenergies, which we finally needed. So it is more belletristic and verbal explanations. We get to formulas, but there is no reason to write equations when you do not have an idea why you need to go on with function. So we need eigenenergies. We do have Hamilton. We have eigenstates. How do you find energy state? How do you find value of observable if you know the operator and you know the wave function? I don't know how to convince Brian and Ket. You multiply operator of the observable with wave function conjugate, integrate, and get the value. There are no restrictions to this rule. Or maybe there are, but I'm not aware. So if you take an eigenstate from left and right, put Hamiltonian in between, and Hamiltonian is rate of what? Hamiltonian operator of which energy?
Oh.
Okay, good. So if you put into this construction for extraction Hamiltonian and eigenstates, you'll get eigenenergies. Right? Or you can plug in your eigenstates into time independent Schrödinger equation and then energy. So it is quite doable exercise. Since Hamiltonian includes this differential operators, one can practice taking them. And then by the whole, is it okay just to discuss whether I need to write it? Give me a little sign if you want to exercise a little. If you want me to exercise a little writing. Right. So if we have this phi not phi 1 phi 2 of as functions of x, we can plug either of them into time independent Schrödinger equation. I. We should, and Hamiltonian is what? Set of differential operators. We should get the same function that we believe that we will get, since it is normalized. But there will be additional factor, and the factor that will pop up here will be eigenenergy. So by plugging in different wave functions, you will get this energy. I'm just skipping this exercise, although it is not very good. Next step I will do in a little non-traditional way, but I cannot say that it will be a lot of savings of efforts. Another way to find these energies would be to take I and it will give energy of eigenstate energy. And these two ways do not contradict, right?
These are absolute values of the H.
Yes, expectation values of the H in case our quantum state is in the, our quantum system is in the eigenstate. And you already know this eigenstate. So this is more, like I say, traditional way. If you would need to answer to a stranger about eigenstates or teach this course yourself, this may be most correct. I will do it, I wouldn't say incorrect, but a little different. So, you remember how we were introducing raising Fourier operators? So was there any personality involved? Like a sticker? Weather. Right. So it's, there were some general concepts. Like, this weather operator can climb only once they're up, once they're down. Applying, going up and down one after another will give the level where we are at, and some additional, and you can get lower than the ball. Did we practice connection between ladder up, ladder down, and Hamiltonian? I hope.
Isn't it if you go up and down, like one on the other?
Yes, yes. But there was one more thing. The weather operators are described as superposition of position and moment, right? And if you have nothing to do during the weekend, and you suspect me in contriving any exams, which probably I'm not contriving, but just in case, if you want to look through your notes and propose something, try to recall the definition of creation and initiation operators. It's something that I'm forgetting myself, and then I need to recall the exact proportionality coefficients in front of p and x, or x and zero. So there are something like square root of mass, frequency, contact, right? And where did we get this factors in front of position and moment when we were defining weather operators? I'm not sharp enough. So there is a definition of weather operators in terms of position and momentum. Position plus momentum will be inclination, position minus momentum will be inclination, but it's not plus and minus. There are coefficients. what are those coefficients? Where did we take? Where should I look through the notes if I was taking notes? Or where should I look on the line if they are recording? Where should I look in Wikipedia maybe? Or what's the logic if I'm having a pen paper and I'm alone on the internet? Probably I will not survive long, but before in the last minute of my life I was just find manipulation of road. So to my memory, we were putting coefficients as unknown variables. Then we were multiplying creation by manipulation on one side and true Hamiltonian on the other side. And then we were solving for with some conditions for these coefficients. Okay? So on one hand, regular Hamiltonian cast as differential operators, on the other, product of creation and annihilation. You are not complaining, which means you totally agree. So I do not remember if we arrived to this equation yet, and if we didn't, I want to do this. Or no? Did we arrive to the top of this? Yes. Yes, you recognize it, right? So if we are in the space of eigenstates, then matrix element of the creation operator will be delta, which is not on the diagonal, but it is on the subdiagonal or upper, right? So what I would be happy to arrive to as an intermediate step is to find out matrix elements of Hamiltonian. I would be happy to cast the Hamiltonian in terms of this prime at vectors. And I don't know why I'm writing it here. It looks like an answer. It should be already derived. If not, I'll try to provide some arguments why it looks this way. So let's discuss it more on discussions side rather than derivation, and then I'll check it if you need to do it. So the requested properties of weather operators are that if you climb one step up, one step down, you stay at the same place where you were, right? So if you want to set up an operator that will keep you at the same place where you were before, you put it theoretic product ket times bra. Right? If you do ket times bra, it will be operator instead of number or whatever. And we start in number k and you end, which means it will not change the wave function. The number here corresponds to the level, the index of the weather step. So if you apply this operator, we will not change wave function, but we will get a number of weather steps as an output. Plus 1. and then everything is multiplied by energy corresponding to the frequency of this oscillator. Plus of 2019, it is our Hamiltonian. Hamiltonian is our plus 2019. We are introduced to each other. And if you want to write down this algebraic form in a matrix form, it will be zeros everywhere except diagonal, and on the diagonal it will be 1/2, 3/2, 5/2, 7/2, okay? And the frequency of oscillation outside.
The red writing on the right side of that, is that part of that equation as well?
No, no,
No.
it's a common. So there are two things that we want to accomplish. And I'm not sure that we will accomplish both, but at least it is a goal. This one is quite trivial. We are chewing on it for again and again. We are slowly approaching so that the energy of the ground state of harmonic oscillator is not zero, right? And by now it doesn't surprise you. You have seen it for the particle in the box. So it's a quantum nature. No momentum, but energy is non-zero, right? So it's 0 point energy, and it is half of the frequency times Planck constant. So it will be trivial, but I need to keep on giving some supporting statements for this observation, because it will come up in your other courses, like chem2 and sprint. There will be problems on several oscillators, finding statistical summations. The second goal, which I really want to achieve, but I doubt that it is possible in the remaining time, will bring us very, very close to originally declared goal, to the goal to predict how the Gaussian distribution will oscillate in the harmonic potential. And right now I'm already knowing the answer and how it will oscillate. But generally, what will happen with a non-equilibrium state of harmonic oscillator, if it is prepared in a superposition of eigenstates rather than a single eigenstate. So here I will spend some time on the math, and analysis will come a little bit later. But the mathematical challenge that I will offer you to solve, follow how it is solved, is formulated in the following way. What are the eigenstates of annihilation operator? I was already speaking motivation too long, so I'll stop about motivation right now, but there is a very strong motivation for this problem. Fine, you know that there are eigenstates of Hamiltonian. They are just eigenvalues. There are, when we were looking in the free space, we were looking at eigenstates of momentum operator. Those are about plane waves. If we are looking on angular momentum eigenstates in hydrogen atom, we will get this SPD shapes. So we always find eigenstates of something. For the oscillator, it will be really beneficial to find eigenstates of annihilation field. Just giving you general directions. And they will be pursued in a form of superposition of all eigenstates with unknown coefficients. So in some sense, we will need to find these coefficients. I don't know about you, I'm already tired. It's too much new material for one person. Who was teaching us how to plot matrices? At the presentations number 2. How to visualize. Okay, so you did better than myself. I was trying to scratch it, this was success. But if you take this Hamiltonian in discrete space of eigenstates, it will be like a set of not a very low height building and then go into skyscrapers. And then diagonal. Do you need comments on this, or if it is nature of your mathematical language? This is a like very trivial, simple thing, but I was also angry on my instructor when I was in the so I don't want you to be repeated, so I'll probably give comments even if you. So when we yes, please.
So is it multiplying it by itself? Oh, so it's like multiplying it by itself. So just a fan constant. Or is it kind of like a conjugate? Just like
Understand the question? I have an answer, but
Inverse or the trans.
yes.
What is that word that I'm looking at? Trans, isn't it just the transpose of identity?
Vector. If you have vector or eigenstate in the discrete space of vectors, you have Pauling vector, you apply transposition, it becomes row vector. So the Brian Kev, this one is column, this one is row. Okay? If we want to express everything in form of matrix form, then 0 will be column vector 1, 0, 0, 0, 0. The bra for state number 0 will be row vector 1, 0, 0. Okay? And if you multiply row by column, you get a number. If you multiply column by row, you get a matrix. If you multiply this column by this row, the matrix will be 0 everywhere except the top one element. Okay? If you do the same game for state number 1, the non-zero element will be on this position here, and in this position here. Everything else will be 0. If you multiply column by row, it will be a matrix composed of zeros everywhere except on the second on the main diagonal. And if you repeat it again, don't worry, I'll come over from different angles. It's not complicated. We'll get there. And if you add together such products, as a result, you will get a matrix which is 1s on the main diagonals and 0s everywhere. So now I was kind of applying to your sense of linear algebra.
I guess my only question is why isn't it the square of what the number is rather than just one?
Square of
You see what I'm saying? Like why isn't it the second of the four?
I'm practicing a lot of laziness and trying to write as less as possible. Okay, let's put number k here and there. Then on the position number k minus 1, because we start counting from 0, there will be 1. Position number k minus 1. 0, 0, and here will be position number k minus 1. So the number that is placed in this bracket is not a number, it's index, it's position. Okay? Make sense?
Yes, but not the only number that's put in there is like 1 or 0.
Exactly.
Okay.
Yes. Yes. Good. I don't mind your images to be recorded, but I tried my best to focus camera into this. So, what is a matrix that has ones on the diagonal and zeros everywhere else? How would you determine what is this matrix? Identity, right? Acting on a vector, if you reproduce the same vector. So it's basically, it does nothing. Matrix, nothing to do. Okay. So when I don't like my own words from previous years. Maybe I was considering as a joke here a few years ago. It's a little boring, but we already discussed that, right? If you want energy of ground state, you are just following the rule for expectation value. And if you want to formulate it as a joke, you can call it a sandwich of prime. Okay? So it's either wave function star this function, or in matrix form, you do this bra operator. This zero state will be one if the limiting position of the when we do formulate our Hamiltonian as this frequency constant, this ket times bra at 1/2, this 1/2 here should be interpreted as a number times identity matrix. If operator cannot be a number, operator is always a matrix. If you speak in this algebraic sense. So if we see a number, in fact, it's not a number, it's this identity operator. And since we are practicing an attempt to find expectation value, which means we multiply it from left and from right by ground state, we may want to plug this identity operator and then practice this multiplication in the ground state. So, bring some here. So it was only 1/2, and we put this identity operator. Then we put the summation outside of brackets. Make sense? So it was this plus this, and we added it into the result. Now we put summation out of brackets, and we actually can put the cat times bra with the same coinciding indices also outside of the bracket. And this is nothing new. It is our Hamiltonian for harmonic oscillator in this discrete algebraic form. So frequency, constant, summation, and then the thing that will parse on the diagonal element of matrix, and then elements on the main diagonal will run starting from 1/2 and then going strictly within the line. So if we do multiply it by ground state from left and right, we will repeat similar operation again and again. Now it is just a very simple example, and I can announce it a little slower. So we do have this yellow stuff that parses that corresponds to diagonal matrix, and then we multiply it by bra and ket from left and right. So we have four objects total. We can dissect this matrix as product of ket and bra. And now, so before originally, we can look on it as row vector, matrix, column vector, right? But in this notation, one can dissect it in the middle and consider it as row by column, row by column. So when you see this angular brackets looking to each other this way, it means there is a protocol to find a number, to get rid of matrices and vectors and get just a number. So it's orthogonality. Eigenstate number k overlapping with eigenstate number 0. If our eigenstates are orthogonal and normalized, this product will take which values? It should be written somewhere on the top. Yeah, either 0 or 1. On the 0. In which case, if you be 1, for which values of k, this product will be equal to 1?
0.
Yes. Correct. If k equals 0, then this product equals 1. If k is not equal to 0, it will be 0. Same here. This state, ground state, number 0, and this state number k. It is another term per delta. It will be 1 only if k equals 0. So we do this bracket products are always can be always represented as delta symbol. Product of product delta k comma 0, delta 0 comma p, which means the stuff under summation will be non-zero only for k equals 0. I don't know about you, I'm super tired. It will be non-zero if k equals 0.
So does this equal the jumps that we have? Is that what we're
If
doing?
you we'll get to number of you're correct, but here we are looking on something simpler. We are already setting up number of jumps equal 0. We are looking on the lowest state, which has no jumps. We apply this story about jump up, jump down for the lowest state, state number 0. So if k equals 0, then stuff inside the summation is not equal to 0, which means out of the summation we parse only one element corresponding to k equals 0. We remove the summation. And we set up k equals 0. And we remove all vectors. So what is remaining? HR omega k equals 0 times 1/2. Okay? So it's basically a trivial result. We didn't make any discovery. We just reproduced known thing with this ugly algebraic mechanics. For this simple question, it's excessive effort. We do not need it. But for some problems that are much more complicated in regular way, this algebraic approach will be like 100 times quicker. And I don't know why we were looking on other handwriting things of text. Round, unity operator, parsing k equals 0. So ground state energy is frequency on constant 1/2. So one goal is achieved. In the remaining 3 minutes, I want to achieve much bigger goal, which is not possible, but I need to start so that maybe some of you will remember a little bit. I was watching West movie before the teenage, and I already forgotten the movie. Maybe not something important, but there was a adventures when main character needs to penetrate into a tower or to save someone or steal something, and it's like almost bare naked person needs to climb on the vertical tower. And there was a trick to have the anchor from a boat on a rope, throw it up, and then climb on a rope. The attempt to find eigenstates of the annihilation operator is our anchor and rope that will help to describe oscillation of Gaussian wave packet in the harmonic potential. So it's not literally what you're looking for, but it is a very quick, well, nothing is quick, but it's the quickest of possible shortcuts. And the eigenstate of annihilation operator is referred to as coherent state. So this is where we should start when we so when we meet, we don't meet on Monday. So it will be on Wednesday. And the problem that we were solving, representing unknown eigenstate of annihilation operator as superposition of all eigenstates with unknown coefficients. So, and by definition of eigenstate, we have this unknown function in left and right, and here we have operator, and here we have unknown eigenvalue. So basically equation of unknowns. We do not know infinite number of c sub n, and we do not know the mu. But we will be brave enough to try to follow. So the result will be a sequence of values of c sub n and value of mu. And there is a big hope, I guarantee, that we will get success in reproducing this oscillatory behavior with limited amount of time. Have a nice weekend. Thank you for your dedication to course and questions. Send me emails if you want to discuss homework or projects. Have a nice weekend.